Do you think the speed of light is just a number? Almost 300 million meters per second. Fast. Very fast. The fastest thing we know. All right, but why is it the limit? Why can't you go any faster? What stops you? Most people have never really stopped to think about that. They simply accept it. Einstein said, the speed of light is the cosmic speed limit. That's how it works. But that's not an answer. That's just repeating words. When you really ask why nothing can go faster than the speed of light, when you investigate what's actually stopping you, you discover something so strange, so fundamentally different from everyday experience, that it completely changes everything you thought you knew about space and time. The speed of light is not just a speed. It's not just the fastest thing. It's the very structure of the universe. It's intertwined in the fabric of space and time in a way that makes going any faster literally meaningless. Let me show you what I mean. Let's start with something simple, something everyone knows. Things fall. Drop something, it falls. About 5 meters in the first second, to be precise. That's what Galileo measured. Drop a ball, drop a stone, drop anything. In 1 second, it falls about 5 meters. Now the moon. The moon is orbiting the Earth. It is not falling. It's up there, spinning, making a circle. But wait, is it falling? Think carefully. If the moon were standing still in space, not moving, what would happen? It would fall toward the Earth. Gravity would pull it. But the moon is in motion. It is moving sideways, tangent to its orbit. And why is it moving sideways while gravity is pulling it down? It keeps missing the Earth. It falls toward the Earth, but it keeps missing the target. That's an orbit. Continuous falling while moving sideways fast enough to keep missing. This is where Newton had his brilliant insight. The moon is 384,000 kilometers from the center of the Earth. We are on the surface, about 6,400 kilometers from the center. So, the moon is about 60 times farther away than we are. Newton thought, what if gravity weakens with distance? What if it follows an inverse square law? That means if you go twice as far, gravity becomes 4 times weaker. 3 times farther, 9 times weaker. The square of the distance. If that's true, then at the distance of the moon, 60 times farther, gravity should be 60 times 60, that is, 3,600 times weaker. On Earth, things fall 5 meters in 1 second. If gravity on the moon is 3,600 times weaker, then the moon should fall toward the Earth by about 5 meters divided by 3,600. Do the math. 5 meters divided by 3,600, that gives about 1.5 millimeters per second squared. Let me rephrase that. Secondly, something at the distance of the moon should fall toward the Earth by 1.5 millimeters, multiplied by 3,600, because we're talking about the square of time in the formula. 1.5 millimeters times 3,000 and 3,600 is equal to approximately 5 meters. Exactly what we measured on Earth. Newton calculated how much the moon should fall toward the Earth per second if gravity followed an inverse square law, and it matched perfectly. The moon is falling at exactly the rate that Newton's law predicts. That was huge. It wasn't just a theory, it was a prediction. Newton took a completely independent fact, how fast things fall on Earth, and connected it to another completely independent fact, the period of the moon's orbit and its distance from the Earth. Two things that seemed completely unrelated suddenly became connected by a single law. The law of gravitation. There was no turning back. Newton went further. He calculated what the shape of planetary orbits should be if gravity followed an inverse square law. And he found out that it should be an ellipse. And guess what? The planets really do move in ellipses. Kepler had already measured that, but Kepler didn't know why. Newton explained. He got 3 for the price of 2, so to speak. And then more things fell into place. The tides. Why are there tides? Because the moon pulls the Earth. But wait, if the moon only pulls the Earth toward it, there should be just one high tide per day, right? The bulge of water on the side facing the moon. But there are 2 tides per day, about every 12 hours. Why? Some people thought that the Earth was being pulled away from the water. Others thought that the water was being pulled toward the moon. Both were kind of right, but neither understood completely. Newton realized what was really happening. The force of the moon on the Earth and on the water is the same at the same distance. But the water on the near side is closer to the moon than the Earth is. So it is pulled with more force. And the water on the far side is farther from the moon than the Earth is. So it is pulled with less force. So you have 2 bulges where the water is pulled more toward the moon. Another where the water lags behind because the Earth is pulled more strongly than that water is. 2 tides a day. Actually, the Earth does the same trick as the moon. It moves in a circle. The center of the circle is somewhere inside the Earth. The Earth and the moon orbit their common center of mass. If you want, that water is thrown out by the centrifugal force even more than the Earth. That water is attracted more than Earth's average. Anyway, the tides have been explained, and the fact that there are 2 per day as well. Many other things became quite clear. Why is the Earth round? Because everything is pulled inward. Why isn't it perfectly round? Because it's spinning. So the outer part is pushed out a little and it balances itself. Because the sun and the moon are round, and so on. As science developed and measurements became more precise, tests of Newton's law became much more rigorous. The first careful tests involved the moons of Jupiter. Through careful observations of how they orbited over an extended period, it was possible to accurately check if everything was in accordance with Newton's laws. And it turns out it wasn't. Jupiter's moons sometimes seem to be 8 minutes early and sometimes 8 minutes late compared to the schedule calculated by Newton's laws. 8 minutes. That's a huge discrepancy. Something was wrong. But wait. It was noticed that they were ahead of schedule when Jupiter was close to Earth and behind schedule when Jupiter was far away. A very strange circumstance. The Danish astronomer Homer, trusting in the law of gravitation, came to an interesting conclusion. Light takes some time to travel from the moons to Earth. And what we are seeing when we observe the moons is not how they are now, but how they were some time ago. The time it took for the light to get here. When Jupiter is close to us, the light takes less time to get here. When Jupiter is farther away, it takes longer. So he had to correct the observations for the differences in time. And by how far ahead or behind they were, he was able to determine the speed of light. That was the first demonstration that light did not propagate instantaneously. Think about what just happened. We discovered the speed of light not by measuring the light directly, but by having confidence in the law of gravitation. When something didn't add up, instead of discarding Newton's law, Homer said, "What if light takes time to travel?" And he was right. I bring this specific subject to your attention because it illustrates something important. When a law is correct, it can be used to discover another one. If you have confidence in this law, then when something is wrong, it may suggest some other phenomenon. And if we didn't know the law of gravitation, it would have taken us much longer to discover the speed of light, because we wouldn't know what to expect from Jupiter's satellites. This process developed into an avalanche of discoveries. Each new discovery provides the tools for many more discoveries. And this is the beginning of that avalanche, which has been continuing for 400 years without stopping. And we are still in the midst of the avalanche at full speed right now. But here's the thing. Once you know the speed of light, once you measure it, you start to notice something very, very strange. Imagine you're on a train. The train is moving really fast. Let's say half the speed of light. You turn on a flashlight pointing forward, in the direction the train is moving. Common sense says that the light should now be traveling at the speed of light plus the speed of the train. Just like if you throw a ball forward on a moving train, the ball moves faster than if you threw it while standing still. But that's not what happens. You measure the light, and it's still traveling at almost 300 million meters per second. Exactly the same speed. You think, okay, maybe I measured it wrong. So you speed up the train even more. 90% of the speed of light. You turn the flashlight on facing forward again. You measure. Still the same speed. You get frustrated. You speed up the train to almost the speed of light. You turn on the flashlight. You measure. Still the same value. The speed of light doesn't add up. It doesn't combine with your speed. It's always the same. It doesn't matter how fast you're moving. That should break your brain. That's not how speeds work in everyday life. Speeds add up. If you're on a train going at 80 kilometers per hour and you walk forward at 5 kilometers per hour, you're moving at 85 kilometers per hour relative to the ground. But light doesn't do that. Light always moves at the same speed relative to you. It doesn't matter how fast you're moving. Why? Einstein realized what was happening, and it's so strange. So contrary to common sense that even now, more than a century later, people have difficulty accepting it. Time and space are not fixed. They are flexible. They bend and stretch to keep the speed of light constant. When you move faster, time slows down for you. Your clock literally ticks slower, and distances contract. The space in front of you gets compressed. These effects are real. They are not optical illusions. They are not measurement errors. Time really does slow down. Space really does contract. And the amount they change is exactly the right amount to make the speed of light the same for everyone. Let me repeat that. The universe adjusts time and space. It bends them, stretches them, compresses them to ensure that light always travels at the same speed for everyone. The speed of light is not just a speed. It's a structural constant of the universe. Space and time are arranged in such a way that this speed is the same for everyone. Now, it gets even stranger. If you try to accelerate something, anything, to the speed of light, something very bizarre happens. The closer you get to the speed of light, the harder it gets to go faster. It's not that you run out of fuel. It's not that your engine isn't strong enough. It's that the object itself resists acceleration more and more. We call this relativistic mass increase. As you go faster, your inertia increases. It gets harder and harder to push you faster. And as you approach the speed of light, your inertia tends toward infinity. To actually reach the speed of light, you would need infinite energy, which is impossible. So, nothing with mass can ever reach the speed of light. Not because of some arbitrary rule, not because of engineering limitations, but because the very structure of space-time prevents it. Light can travel at that speed because photons have no mass. Zero. Massless particles can travel at the speed of light. In fact, they must. They have no choice. They're always moving at that speed, but anything with mass can get close. Very close. 99.9% of the speed of light, but never exactly there. The universe doesn't allow it. Now, you might ask, but why? Why is the universe organized this way? Why is there a speed limit after all? And here's the answer that's going to frustrate you. There isn't a deeper reason. The speed of light is not a speed limit imposed on the universe. It's a consequence of how the universe is structured. Space and time are not separate. They are intertwined in space-time. And space-time has a geometry, a structure, and this structure has a built-in conversion factor between space and time. This conversion factor is the speed of light. It's not that light is special. It's that space-time has a maximum rate at which cause and effect can propagate. Light, incidentally, travels at that rate because it has no mass. But the rate itself is a property of space-time, not of light. If light didn't exist, the speed limit would still be there. It's a characteristic of the universe itself. Here's another way to think about it. In everyday life, you think of space and time as separate things. You move through space. Time passes. They are independent, but they're not. You are always moving through space-time at a constant rate. Always. But this movement is divided between space and time. If you are standing still, all your movement is through time. You are moving into the future at maximum speed, 1 second per second. But if you start moving through space, you have to divert some of that movement from time. Now you are moving through space and time, which means you are moving through time more slowly. The faster you move through space, the more slowly you move through time. And there is a maximum. If you could move through space at the speed of light, you wouldn't have any movement left for time. Time would stop for you. That's why light doesn't experience time. From the photon's perspective, it is emitted and absorbed at the same instant. No time passes. The universe is frozen. You can't go faster than light because you can't have less than zero movement through time. That's the limit. That's the barrier. And here's the beautiful part. This isn't just theoretical. We've tested this over and over again. Particles and accelerators are accelerated to almost the speed of light. And guess what? The closer they get, the harder it becomes to accelerate them even more. Exactly as predicted. GPS satellites have to take time dilation into account. They're moving fast and they're in a weaker gravitational field. So time passes differently for them than it does for us on the ground. If we didn't correct for that, GPS would be off by kilometers in a single day. Muons created in the upper atmosphere by cosmic rays should decay before reaching the ground. Their lifespan is very short. but they are moving close to the speed of light, so time slows down for them. From their perspective, they live long enough to reach the ground. From our perspective, they live longer because they're moving fast. Either way, more muons reach the ground than they should, exactly as relativity predicts. It's not speculation, it's measured. The speed of light being a limit is as well tested as anything in physics. So let's put it all together. Why is the speed of light the limit? Because space-time is structured in a way that cause and effect can only happen up to a maximum rate. That rate is the speed of light. Not because light is special, but because space-time itself has this built-in conversion factor between space and time. You can't go any faster because going faster would require moving backward in time, which doesn't make sense. You can't have negative time. You can't undo cause and effect. The speed of light is the speed at which the present propagates through the universe. It's the speed at which information can travel. It's the speed at which forces act. It's the maximum rate of change. And this process, this avalanche of discoveries, began with Newton discovering gravity by observing the moon. Then Römer discovered the speed of light by observing Jupiter's moons. Then Einstein realized that the speed of light is constant and derived relativity from that. Then thousands of experiments confirming it, each discovery building on the previous one, each new insight opening doors to more insights. That's how science works. It's the avalanche that's been going on for 400 years, and we're still in the middle of the avalanche at full speed right now. The speed of light is not just a number. It's the key. It's the thing that reveals how space and time work. It's the thing that shows us that the universe is stranger and more beautiful than we ever imagined. And the fact that we can understand it, measure it, test it, and use it to make predictions. That's the beauty of physics. Not comfort, not simplicity. Truth.